In this video, I'm going to introduce you to the 7 circle theorems. So I'm going to start with a part of the circle. Now I'm going to draw the circle. So upon having the circle, we have something called the central point. So this is angle at the center, which is equivalent to 360. Now any imaginary line from the circumference of the circle to the center is called radius. We can also call it the quarter of the circle because it does not cut through to the other end. Now the next thing I want to introduce you to is a line from the circumference that passes through the center of the circle and touches the other circumference of the circle is regarded to be diameter. So the diameter is like 2 radii. So the combination of the 2 radii will become a diameter, which is half of a circle. So the diameter is equivalent to 2 radii, so which will give us the half of the circle. Having identified the radius and the diameter of the circle, the next thing I want to chip in is the distance around the circle. In fact, the distance around any shape is called perimeter, but for circle, we have a name for it, which is the circumference of the circle. It means the distance around the circle. So this will make us to know a couple of new definitions. So a line that cuts a circle but that does not pass through the center of the circle is called a chord. Inasmuch the line does not pass through the center of the circle is called a chord. So I'm using a blue line to identify the line to be a chord. As we have the chord, so the inner parts of the chord that we prepared out, which I'm going to paint yellow, is called the segment. We have it as segment. It is the inner part of the portion that we cut off the circle. So the smaller part, which is painted yellow, is called the minor segment, whereas the other part is regarded to be the major segment because it's bigger in terms of size. Now, if we take a slice of the circle, like we cut a cake from the center towards the circumference like this shaded part is regarded to be sector. It's like cutting it across to the center through 2 radii, which is different from cutting it like a chord. This one is passing through the center across 2 radii. Now, let's say I take a point outside of the circle. So from the point, I draw a line that goes straight to the circumference of the circle, but does not cut through the circle. And I take another line from the point, which equally touches the circumference of the circle, but does not cut through. Such lines are regarded to be tangent. So it does not enter into the circle here, so we have it as tangent. So by the time we go into the theorem proper, you should be familiar with all these circle terminologies. So let's go into it. So to theorem number 1, we have the rule number 1 by the left and the example given by the right. So the first theorem states that angle at the center is twice angle at the circumference, which means angle that is coming from the arc at the center of the circle, which is angle B, is going to be twice as that of angle at the circumference A. So in another word, B is 2 of A. If you are struggling to remember that, you can use the arc code. Population at the center of a city is larger than at the outskirts of the city. So we go straight to the example by the right side. We have the circle here and they give us the angle AOC to be equal to 96 degrees, and we are asked to find angle ABC. So remembering that angle at the center is twice the angle at the circumference, that means we are going to divide 96 into 2, which will give us 48 degrees. Easy. Remember, angle at the center is twice the angle at the circumference. So if the question was tweaked to be, if ABC is 44 degrees, so the angle AOC will be twice the angle at the circumference, which makes 44 multiplied by 2, so we have 88 degrees. So let's move on to rule 2. Here's the picture for rule 2. What rule 2 says is angle in a semicircle contains a 90 degrees. That means a triangle that passes through the diameter of a circle, the angle that we are going to have at the circumference is going to be 90 degrees. Technically, this is just rule 1 again, because if you see the angle from the center of the circle is giving us 180 degrees because we have a straight line. And when you have the angle at the center, which is twice the angle at the circumference, that means the angle at the circumference is going to be half of the 180, which is equal to 90 degrees. Apart from using the rule number 1, the rule number 2 is clearly stated that angle in a semicircle is going to be 90 degrees. So in this example, let's find angle ABC. Let's consider that this is the center of the circle and it passes through the diameter of the circle. So the angle B is going to be 90 degrees based on what the theorem number 2 states. Now let's take a look at one more example here. We still have the theorem given here that angle in a semicircle is 90 degrees. So we are given that if CAB is 44 degrees, find the angle BCA. We are looking for the angle C. And if you remember, angle from the semicircle is going to give us 90 degrees. So we have angle 90 at the B. Then from sum of angle in a triangle, which is 180 degrees, so we sum 44 and 90 together to give us 139 degrees. So we are going to remove that from 180 degrees. Then we have our angle X to be equal to 46 degrees. Easy. Now let's move to a new rule, rule number 3. So what rule 3 says is, if you have an arc, like you have it here, yellow, and generates angles in a particular segment, the angles are going to be the same. You can see them painted in red. The angles are going to be the same. So angle from the same arc at the circumference are equal. So let's say we have another line from the arc and generates another angle in the same segment. This angle is going to be the same as the two. So we have another line again. So far the angles are generated in the same segment. The angles are going to be the same. So be mindful not to confuse this theorem for the rule number 1, which states angle at the center is double angle at the circumference. In this case, angle in the same segment are equal. Now let's go to the example at the right side. If angle ABC is 44 degrees, we are asked to find the angle ADC. And if you recollect, angle in the same segment are equal. And most especially when they move from the same arc, which I'm painting yellow here. So angle ABC and angle ADC should be the same. So for clarity, let's try to draw the line. It moved from this to this place, and it also moved from here down to this place. So automatically angle X and that angle 44, because they fall in the same segment, are equal. So angle ADC is equal to angle 44. So in another example, we are given that angle DAB is 44 degrees, and equally angle ABC is 60 degrees. So the question is to find angle DCB, the angle at C, let's call it X, and angle ADC, we call that one Y. Now we have to find the X and Y. Of course, the two are going to be either 44 or 60. It's about getting it right now. So let's start by dividing our arc. We have the arc here. So let's follow the line to see the angles in the same segment. So we have it drawn here down to the D, which will give us 44. Then we have the next line down to the B. So it makes the other angle to be 44 degrees. So we have DCB to be equal to 44 degrees because they are equal. So let's remove all this. Then we divide our arc again. So we have the arc given here. Then we follow the line it goes down, we have 60. So from here down to the arc, we have y to be 60 again. So the angle ADC will end up to be 60 degrees. Easy. Now let's move on to rule 4. For rule 4, we have the theorem to be given as opposite angles in a cyclic quadrilateral add up to be 180 degrees. So for angle A and angle C, they add up to be 180 degrees. For angle D and angle B, also adds up to be 180 degrees. So let's talk about quadrilateral. Quadrilateral has 4 sides, and a cyclic quadrilateral means the angles are touching the circumference of the circle, meaning the quadrilateral are placed in the circle of which they are touching the circumference of the circle. Now let's try to use this example. If ABC is 84 degrees, so angle at B is 84 degrees, and BCD is 102 degrees, so we have the angle 102 degrees here. So we have to find the angle CDA, let's call it X, and also angle DAB, we call that Y. And this is a cyclic quadrilateral because the edges touches the circumference of the circle. So recall, opposite angles must add up to be 180 degrees. So y must be whatever value that will make 102 to be 180 degrees. So that makes it 78. Similarly, we have it for x. So what adds up to give us 180 will be 96 for x. And now let's take a look at another kind of question. Here we are asked to find, is this quadrilateral cyclic? And we should explain our answer. So we have a quadrilateral given here. So for me to solve this, I may decide to first draw a circle around it and try to fix the circle across the edges of the quadrilateral. So you can see that it's not really working, and honestly speaking, this is not the right approach to identify if truly is a cyclic quadrilateral. But what I know is that opposite angles of a cyclic quadrilateral will add up to be 180. So by the time I try to add the two together, I will end up with 179 degrees. So automatically, this is not a cyclic quadrilateral. So the answer to that is no. So here is the rule 5. It's called the alternate segment theorem. It says whenever you have a tangent, remember tangent is a line that touches the circle at one place here. So when a tangent meets a chord, and this is a chord, remember, and the chord is the line that cuts the circle but does not touch the center, then the angle that it makes with the tangent is equal to the opposite angle in the resulting shape. You can see the angle here. And similarly, from the other side, the tangent meeting the chord, this side, must be equal to this opposite angle. So we have it given here. And mathematically, the angle between a chord and a tangent is equal to the angle in the alternate segment. So here is an example. If BAD is 19, B to A to D is 19, they want to know what ACB, A to C to B, this one here. But we got a tangent here, so meeting a chord, and it meets at 19 degrees. So the angle at the alternate segment, that one must also be 19. It's as simple as that. Now, they didn't tell us, but let's imagine that this one here is 104 degrees. This is a tangent meeting a chord at 104. So the angle in the alternate segment opposite here must also be 104. Okay? And that is rule number 5. Finally, we have rule number 6 and 7, and we are going to do this all in one, and we have a couple of examples. So here's the picture for each of the rules. And rule 6 tells us when a tangent, a line that touches the circle, meets a radius, they always meet at 90 degrees. They always make a 90-degree angle. Here is the last rule, rule number 7. It tells us There are two tangents to a circle from the same point in space. Here's the space, so I'm drawing a tangent to that circle. Okay, so it's touching here, so it keeps going, it won't touch anything. They are the same length. They will always be the same length. Now let's have a go at a couple of questions. PT is a tangent at T. TU is a chord. Here is our chord. And angle PTU is 54. Find the size of angle TOU. So this angle here. TO is obviously the radius because it's a line from the center to the circumference. When a tangent meets a radius, the whole angle is 90 degrees. If that whole angle is 90 degrees and this part is 54, this must mean this angle here is equal to 26 degrees. So here is a triangle made of two radii and the two base angles must be equal. So this one will also be 26 degrees. And to get the angle at O, we do 180 minus 26 and it will give us 128 degrees. So this one is 128 degrees. So for clarity, tangent meeting the radius is going to be 90 degrees. So this will make us to have the angle 26, and as it is an isosceles triangle, we have angle 26 here too. So angle O is 180 minus 26 minus 26, which will give us 128. Last question. PA and PB are tangent to a circle. We know that two tangents coming from the same point, when they meet a circle, they must be the same length. So that length is equal to that length. So we got an isosceles triangle. So this angle is 68. So PAB, we have to get that angle. Do you know that if this and this are the same length, then these angles are going to be the same? So this must be x and this must be x. So we try to find that. So we know that 2x plus 68 must be equal to 180, sum of angle in a triangle. And so 2x must be equal to 180 minus 68, which is 112 degrees. So x must be half of that, which will give us 56 degrees. So the angle at the P is 56 degrees. So those are all the 7 circle theorems. I believe this will be helpful in your learning journey of the circle theorem. If you are new on this channel, kindly click the subscribe button and help me reach 20,000 views by sharing this video. Till next time I see you, I remain yours, Maths Made Easy.